Hi guys, John the Quant here. This is week 3 of the free data science bootcamp. If you didn't start with week 1, a link should pop up over here, and I highly recommend that you go back and start there. There's going to be a link in the description as well, okay? Now last week, and look for a pop-up again, we looked at the distribution, or the shape of the data, and we talked about what we wanted the shape of the data to be, and we figured out an intuitive way to make predictions from data and estimate how accurate our predictions actually are. Now, in general, we said that we wanted our data to be symmetrical, because then all of the measures of center were at approximately the same place. Now, this week, we're going to figure out how to take data that is not symmetrical and how to make it more symmetrical. We're going to change its shape to make it more symmetrical. We're going to learn a few ways to do that, and then we're going to do some more investigation of the data, and we'll talk about other properties that we want our data to have and how we can further change the data to make it more like that. Let's go to the computer and get started.
All right, we're looking at how to transform features. First thing, we're loading the data. This is the same diabetes data that we've been working with in the lessons this whole time. And I usually start off by just looking at histograms. Right? Looking at histograms helps with several things. First off, it's going to let you see if you've got a nice hump or anything like that. It's also going to let us look at potential missing values and data quality problems like we saw last week. So these are almost the same. We're seeing these spikes at 0 that we don't think are supposed to exist. And this one is very heavily skewed, as is this one. And the outcome is not exactly balanced, but it's not too bad. So the first thing that we need to deal with is missing values. All right, it's super common that data sets have missing values. Pretty much all of them do. And so you've got to figure out what to do in that case. You can't just ignore them because that's not how models work, really. All right, you've got to figure out, what am I going to do about this section here where BMI is listed as 0, and it's clearly not correct. So the first thing we're going to do, I'm setting up a tracker here so that we can keep track of which transformations we make and how we handle everything, and that's just going to help us later on, you'll see. So I'm looking here and we're seeing missing values, right? Like I said, the spikes at 0 that we don't think are supposed to exist. And those are really obvious on a histogram, which is why I like exploring my data with histograms so much. I've made some notes here on each column. All right, it's unlikely and possibly impossible for a person to have 0 blood glucose. Pregnancies, though, lots of women have had 0 pregnancies, so it's really hard to tell if this abnormally large spike here at 0 is real or not. We can't really tell, so we're going to have to treat it as if it is correct. Same sort of things going on. Blood pressure, nobody gets 0 blood pressure, so we're going to say that zeros are missing values. Skin thickness, I don't understand the skin thickness scale, so I'm going to say that based on how it looks in the histogram itself, up here, it looks really out of place. I'm going to say that zeros are missing values there. BMI, insulin and BMI both, I don't think you can have zeros for those, so we're going to treat zeros as missing values there as well. And that's kind of the end of it. So in this cell, we're just going through all of those ones that we said: glucose, blood pressure, skin thickness, insulin, and BMI, and we're saying that if it's equal to 0, just replace it with np.nan, which is not a number or a missing value. And then we can check and see how many missing values we actually have. So there's a whole bunch of them. See, in insulin, it's supposed to have 768 non-none values. It now has 394 because we replaced zeros with missing values. Or if you don't like using info and having to do the subtraction, you can use .isNot.sum, and that's going to tell you how many of them there are. So like insulin is missing 374 values, glucose is only missing 5, BMI is missing 11, and so on. Now we can actually decide how to deal with them. So if you have enough data, you can just drop all of the rows that have missing values, and in my opinion, this is often the best way to handle missing values, but if there are too many missing values, then it's going to delete too many rows. So like here, insulin 374, that's more than half of the data, right? So we can't just drop half of our data. That's no good. But we could lose 11 rows for BMI or like 5 for glucose, and that would be okay. So that's what we're doing here. Dot drop na dot subset equals the list of glucose and BMI. That's going to just get rid of the columns that have either glucose or BMI missing. And then I'm setting up the missing values tracker dictionary to just remind myself that I had just dropped the missing values from those columns. Then looking at it again, instead of 768 rows, we now have 752, right? Because we dropped, I don't know what the difference is there, 17 or something, 16, that had missing values. And now we're missing 28 blood pressure values, still over 300 insulin, so we got to just kind of keep moving. The next thing after dropping rows is just to replace the missing values. You can replace them with the mean or with the median or some other number that you think is a good baseline, just a good stand-in for when you don't know. Now usually that is the mean, especially if your data is already symmetric, then using the mean tends to work out pretty well, as long as, again, you don't have too many missing values. If we were to replace half of the data with the mean for insulin, then we'd end up with this weird spike, like right in the middle, and then everything else would look all messed up. So we can't do it with insulin, but blood pressure, we only have 28 missing values, so we can definitely do it there. And that's what we're doing in this cell. So we've got BP mean, that's the mean of the blood pressure column, and then we're setting the column equal to itself, and then we're saying dot fill na with the mean. So fill na means it's going to fill all the missing values with this number, whatever the mean is. And I'm just making a note of that again in the tracker. And now if we look again, blood pressure has 752 non-null values, so all of the missing values there have been filled in, and all we've got to deal with next is insulin and skin thickness. And here we've got a histogram showing when we replace the missing values that were zeros in the blood pressure column with the mean, we end up with this nice kind of nice looking symmetrical hump shape, which is pretty much exactly what we want. Now what are we going to do for these ones that have a lot of missing values? We're going to use imputation for those. Okay, so imputation is like the most complicated way to fill missing values, at least that we're going to talk about. And the basic idea of imputation is that you're going to use the data that is not missing to create a machine learning model, and then you're going to use that model to predict the values that are missing. So when you impute missing values, you're going to use the information you've got to generate more information. And the downside to this is that you don't really get to know how accurate your predictions are or how true the new information is. So if it's bad information, it can lead to making bad decisions. But I mean, imputation is a really powerful idea, and it's worth trying when you need it. And like, we need it now. We need skin thickness and insulin. We think they're going to be really important for predicting whether a person has diabetes, but we're missing way too many values to do anything else. So we're going to use imputation to do it. And scikit-learn, which is a very nice package you ought to install, scikit-learn, SCI-KITLEARN, scikit-learn, has two relatively easy, it has a bunch of other imputers actually, but we're going to look at two here. KNN imputer and iterative imputer. So the KNN imputer, KNN stands for K nearest neighbors, and that's a pretty simple machine learning model where you're just using like the closest data points to predict the missing data. It works really well, and it's typically pretty quick. All right, we're going to talk a lot more about KNN in a couple of weeks. For now, we're just going to use the KNN imputer object and let it do all the work for us. The iterative imputer is still experimental, but in my experience, it works pretty well. So it can use a bunch of different models, and especially ones that take advantage of relationships between features. Now that's the important part. It can take advantage of relationships between features. Like KNN doesn't take advantage of that. It just says what are the nearest data points in, if you consider all of the features, what are the nearest data points. Whereas the iterative imputer is going to be like, if say down here we've got glucose and skin thickness have some kind of relationship. It looks like that might be the case. Or BMI and skin thickness, right? It looks like there's a linear relationship there. Well, an iterative imputer can take advantage of that. So it can be, but isn't always, a much more powerful way to impute missing values. So I'm looking at this pair plot that I was just alluding to. And the reason I created this is to see if there might be relationships that the iterative imputer can take advantage of. And some of them, I mean, I just mentioned BMI and skin thickness, but glucose looks like it might be related to insulin in some way. And even down here, age maybe and insulin could have some kind of relationship that perhaps the iterative imputer could take advantage of. So down here, and because the iterative imputer is experimental, you have to turn it on. So you have to do from sklern.experimental import enable underscore iterative underscore imputer. And then from sklern.impute, we're going to import our KNN computer and the iterative imputer. And I went ahead and did both. I just started up a KNN imputer and then did this fit transform. The reason I'm doing it this way, so fit underscore transform, it both fits the imputer and also transforms the data all at one time. So fit is like when you use .fit, you're telling the model to learn how to make predictions. And then when you use transform, you're telling it to actually change the data. But scikit-learn has this pretty easy process where you use fit underscore transform, and it does both at the same time. So this is going to fit the KNN model to the data, and then it's going to transform the data and fill in the missing values. And we're doing the same thing down here in iterative imputer. Now the default in an iterative imputer is Bayesian ridge regression, which is a form of linear regression, and this is what we're going to talk about next week, linear regression. So it's going to be able to capture like the relationship here between BMI and skin thickness. It's going to capture that really well. So that's why I just left it on all the defaults there. And it uses the same thing, .fit transform, fit underscore transform to fit the model and then fill in the data. And now I'm just comparing the two. All right. So down here, we've got the orange was filled in with the iterative imputer, and the blue was filled in with the KNN imputer, and they're very similar, right? And then same thing with insulin. Orange is the iterative imputer, and blue is the KNN imputer. And they look so similar that I think it's best to use the KNN imputer. In general, unless you have a good reason not to, you just want to use the simplest model. It needs to be simple and intuitive, and more than anything else, probably explainable. You need to be able to say, why did this missing value get filled with this specific value? And KNN is just really easy to understand. So that's why I think we should stick with that one. So here I said, you know what? We're going to use the k nearest neighbors imputed data instead of the iterative imputer. And then I made a note in the missing values tracker that we use the KNN imputer for both skin thickness and insulin. And there you go. We've filled in now all of the missing data. There are no more missing values in our data set. And we can move on to transformations. So before we really get started doing transformations, let's think real quick about what rules we want for transformations. Our overall goal is to make predictions, and we care very much about the units of the original features, but like any transformation we make is going to change the units. Like if you take feet and you multiply by 12, you get inches. It changes the units. So we really need our transformations to be reversible. We've got to be able to undo the transformation and get the original units back. And we also want to keep the data in the same order. I mean, think about this. We want the highest value in the original feature to still be the highest value in the new feature, and we want the second highest value in the original feature to still be the second highest value in the new feature, and like so on, right? I mean, if you mix all the data up, you've just scrambled the data, and it doesn't have the same information as it did before. So we need it to like maintain the directionality, I guess, I'm not sure, of the data. Preserve the rank, there we go. We will need it to preserve the rank of the data, and we need to be able to undo anything that we do. And also we know that we want to change the shape of the data, so we can't just like add or multiply or divide, because that'll move it or it stretch it, but it won't change the shape. So let's keep all of that in mind and figure out what transformations do work. Now, like we did with the missing values, I'm going to create a transformation tracker so that we can keep track of what transformations we're making, and we'll use this later on as well. So pregnancies. We've got this skew right here. It's clearly right skewed, and when data skew to the right, what we want is for it to grow slower. All right, so let's look at these two graphs. This is the graph of just a square root, and this is a graph of a logarithm. And you'll kind of notice that they start by growing quickly, but then they grow very slowly. All right, the square root grows pretty slowly, and the log grows very slowly. And they're kind of the opposite of what we want here, right? So you can do a log transform or a square root transform on any right skewed data, and that should help it be more symmetrical. And we're going to try them out. All right, so the log transform is like the most common transformation in all of statistics, and it works really well when the data skew to the right, which comes up a lot. And it has some nice mathematical properties that make it easy to work with, but that you don't really need to worry about. Now, the hard thing about a log transformation is that it requires all of the original data to be greater than 0. It cannot be equal to 0, right? And it can't be negative. And we know that pregnancies is equal to 0. So in order to fix that, we're going to add 1. We're going to do pregnancies plus 1, and then take the logarithm, which we would have done right here. np.log of filled underscore data pregnancies plus 1. Now the square root transform is probably the second most common transformation. It's less harsh than the log transformation. See, less harsh than the log transformation. So it's really good for when the data is only a little bit skewed. And it can handle zeros, so you don't have to add anything. And when we try them both, this is the original shape, comparing the mean and the median. And then the log transform, it's looking a little better, but there's still some distance between the mean and the median. And then the square root transform, it looks, honestly, I don't think it looks better than the log transform, but the mean and the median are right next to each other. And you can also calculate a quantitative number for skewness, and the way you do that is you just take your column and you do dot skew, and that'll print something out. So like the original skew for pregnancies was 0.9, and the skew of the logarithm was negative 0.24, which means that the logarithm was a little too powerful, and the square root, that was negative 0.15, so it's still a little bit too powerful. But what you want here is for this number to be as close as possible to 0. So based on this, it looks like we are going to be best off using a square root transformation, so that's what we're going to do. So I've created this transformed underscore data frame, and it's just a copy of filled data at first, but then I'm changing the pregnancies column to be the square root of the pregnancies column. And I'm also keeping track that we took the square root. For the pregnancies column, we did a square root transformation in the transformation tracker. And I'm using a list here because there are times when you want to do more than one transformation. Now we're going to go a bit out of our way real quick and talk about standard scaling. And this is another transformation that we want to make. You pretty much always want to make a standard scaling transformation to any numeric column. And what it does is so this is what you're actually doing. All right, subtracting the average and dividing by the standard deviation. Don't worry too much about that. Basically, what you want to do is you want to get it centered above 0, and you want to control how far away from 0 it really goes. So look at this up here. It's centered around, like, what is this, 1.7 or something? Okay, and it's kind of spread out between 0 and 4. Whereas after the standard scaling, it's centered at 0 and spread out from like -2 to +2. Do you see that? And that's what you want. You pretty much always want your features to be centered above 0 if you can make it happen. There's a lot of good mathematical reasons why you want to do that, but if you just think about this, if you add up a bunch of zeros, you end up getting 0, and that makes a lot of stuff in the underlying mathematics work out really nicely. So here we've transformed it using the standard scalar. So this is from scikit-learn. So it's from sklearn.preprocessing. We're importing standard scalar. And this works the same way as the imputer. So you create it, and then you do .fit_transform. And you can actually do a whole data frame at once, but since we're just showing you right now, I just did it on the pregnancies column only to show you what it works out as, and it looks basically the same as when I did it by hand. Now, importantly, we can undo all of this, and scikit-learn makes that easy as well. So once you've transformed it, you can undo that by doing .inverse_transform. So we're using the same scalar object called pregnancy scalar, but now we're doing .inverse_transform on the transformed column, and that undoes it. See how it's moved it back to be centered over like 1.7 and to spread from like 0 to 4? And since we took the square root, we can undo that by raising it to the power of 2, right, by squaring it, which is done right here. And when you look at the whole thing, we started with the transformed, completely transformed and scaled, centered above 0. And then when we undo all of the transformations, so that's do the inverse transform and then square it, we end up back here like this. It looks very similar, and if you lay them on top of each other, they are exactly the same. All right, so in terms of prediction, when you look at this, you want to probably predict that the number of pregnancies of a random person is 0. But this isn't pregnancies, this is transformed pregnancies, and it doesn't really have units. So the number of transformed pregnancies you predict is 0, but that actually matches up with about 3.85 actual pregnancies. See here? So the transformed prediction is 0. The inverse transformed prediction is 3.85. Does that make sense? You've got to get your prediction and then change the units back to the original units. All right, let's look at glucose now. Glucose is pretty symmetrical, right? So all we really want to do is do a standard scalar on that, but what we're going to do is we're going to make everything as symmetrical as possible, and then we're going to use one standard scalar on the whole data frame at the end. So for now, we're going to do nothing. So I've saved this in the tracker as none. Let's look at blood pressure. Same thing, right? It's pretty symmetrical. So I've saved this here as none. Now skin thickness. There's just a little bit of skewness. So I want to try a square root transformation. And I don't know, it looks nice. I think it helped a little, right? So the original skew was like 0.7, and then after the square root, it's negative 0.09. So this definitely helped. So we're going to keep the square root transformation. And we're going to track that in our transformation tracker. Oh, insulin is definitely skewed, right? So in this one, I tried both a log and square root transformation. And in this case, like the log looks pretty good to me, I think. But let's try quantifying that. So down here, the original skew was like 2.15. I mean, look at this, very skewed, right? And even though the log transformation looks a lot less skewed, it's probably just because we're comparing it to this, because its skewness is actually negative 0.24, which is still pretty big. It's not huge. We could probably work with this if we wanted to. Just leave it and be fine, but we can do better. All right, the square root skew was still really big, so we just didn't use that one. So we're going to try an even more powerful way to remove skew. This is called the Yeo-Johnson transformation. And it uses a pretty cool but pretty complicated formula for changing nearly any distribution to a standard normal distribution, which is exactly what we want. Standard normal is the bell shape centered over 0. Now that's exactly what we want. And it's actually really easy to do this transformation in Python because scikit-learn has an implementation. All right, so this is from sklearn.preprocessing import power transformer. That's the one that we're going to use. So when we make the power transformer object, we'll say method equals Yeo-Johnson. Now, this is actually the default, but I like to be really explicit with this one because there are times when you would want to do a different one. So I like to be really explicit with it to make sure that I know what I'm doing. And then it uses that same .fit_transform as before. And when we look at that, now that looks like all the skew is gone, and it is. The new skew is 0.0082. So that took the insulin column, which remember was like really skewed, and it got rid of that skew and it centered it over 0, and that just looks great. Now let's make sure that it can be undone. So to make sure it's going to be undone, we'll use the .inverse underscore transform on the transformed column. And look at that, it goes right back to normal. Good, right? And so let's track that. We use the power transformer with the Yao-Johnson transformation. I'll put that in the tracker. All right, BMI. BMI is a little skewed. We'll try the square root. We'll try the logarithm. Honestly, they both look pretty good. Numerically, though, the log skew is closer to 0, so we'll use the logarithm version. And we'll keep track of that in the transformation tracker. Still moving on, the diabetes pedigree function, it looks very skewed. It looks really skewed. Do you think we're going to use the Yao-Johnson transformation on this again? Honestly, I don't remember. But let's find out. So the log has this weird lump thing rather than a regular hump, so that's not great. But the square root is not even symmetrical, so that's certainly no good. I guess I decided to just use the logarithm. Alright, I said let's just use the logarithm. Sounds good to me. Age, definitely very skewed. Tried log, tried square root. It really didn't do anything, so we're going to go to the big guns, the Yao-Johnson transformation. And so we're doing the same thing. We're starting up a power transformer with the method equals Yao-Johnson, and then we're doing a fit transform on the age column. And when we plot that, it doesn't look normally distributed, but it's kind of centered over 0, and it looks almost uniform, right? So it's definitely a huge step in the right direction from this super skewed age to this somewhat symmetrical thing, right? And you can see that it changed the original skew from being more than 1 to being about 0.15, which is a good deal. But it didn't quite eliminate the skew, but like sometimes that's just the best you can do. And we've got some options in this situation, right? So we could just assume that this is like symmetrical enough. It's good enough, we can use it. And that works fine in like most situations. Another option that I like is to bucketize the age column, okay? And that means splitting people into groups based on, in this circumstance, how old they are. And you should, in general, have a good reason to bucketize something. And we kind of have a good reason, right? Like people in their 20s, they rarely get diabetes. And people like maybe that are older probably get it more often, right? So it kind of makes sense to split people into buckets here. We could also try additional transformations, and it's pretty uncommon for additional transformations to help after the Yao-Johnson transformation, but I mean it does happen. So what I decided to do here was to bucketize. And I decided to use 3 buckets. And they're pretty simple, conceptually simple buckets. Either you're under 30 years old, you're in your 30s, or you're 40 or older. And that's it. And when I think about what little information I actually know about diabetes, like that, those splits make sense to me. People in their 20s rarely get diabetes. People 40 and older sometimes get diabetes, and people in their 30s, I guess, are in the middle. I don't actually know. This is one of the situations where it really pays off to have a lot of domain-specific knowledge. Like if I was a diabetes expert, I would probably know where those splits ought to happen. And I'm not, so I'm just guessing at 30 and 40. Some kind of emergency outside. Right, so to split them, I used pd.cut. So this says go into the pandas package and get the cut function, and I'm cutting the age column of the filled data frame. My buckets go from 0 to 30, and then from 30 to 40, and then from 40 to 1,000, because nobody's more than 1,000 years old. And this here, right equals false, means that like 30 goes in the 30s bucket, and 40 goes in the 40s bucket. So everybody goes, it's this strictly less than sign, basically. And I call them under 30, 30s, and 40 plus. And if we just look at a bar plot there of how many observations we have in each one of those buckets, we've got like almost 400 people under 30. We've got about 150 people in their 30s, and like 200 people that are 40 or older. And that's not too bad. We can definitely work with that. So I'm not sure if bucketizing was the right move, but it looks pretty good to me. So I'm going to keep the age buckets column, or I want to make a new age buckets column, because I also want to keep the Yao Johnson transformation of age. All right, so I've created a new column here called age buckets. I've engineered an entirely new feature called age buckets. And I'm going to track that I have a Yao Johnson power transformer for age, and also like that I used pd.cut to make buckets of age buckets, and I'm also tracking 0 to 30, 30 to 40, and 40 to 1000 to make it easier on myself later. Last column is outcome. It's zeros and ones. We're not going to do anything to it, so I just said transformed data outcome, just keep it the same, and in the transformation tracker I'm doing none. Now that we've got all of our data transformed, we need to finally scale it and encode it. Remember earlier I said we were going to use a standard scaler at the end to just scale the whole data frame at once? Well, that's what we're going to do now. And it's usually a good idea to just use a standard scaler from scikit-learn on like all of the numeric columns. I'm using a very broad generalization there, but that's just to make it easier for you guys to understand it conceptually, and there's rarely a downside to just doing it. So I say just do it. Now, the encoding is because computers don't understand words. They have to convert everything into numbers. So if we have data that's categories, like our age buckets up here, it doesn't know what under 30 means, it doesn't know what 30s means, it doesn't know what 40 plus means. So we have to convert those into numbers before we can work with them. And the most common way is called one-hot encoding, and it's usually the best way to handle categorical features, and it's easy to do with the pd.get_dummies function. Now scikit-learn also has a one-hot encoder, but I like the pandas function better unless it's a really, really big data frame. So since our data frame is not that huge, we're just going to use pd.get_dummies. So I'm looking here, and we've got 752 non-null observations in looks like 10 different columns. All right, which is great. So I've changed outcome to be an integer. I just think it should be an integer. I guess this step probably doesn't matter, but I like it better as an integer. Now I generally find it useful to split my data set into 3 parts. So we'll have the target column. This is the one that if we were building a model, it'd be what we're trying to predict. That's outcome. We're going to have numeric features, all right, which is anything that is a floating point number. So that's like pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, and even age here. All of those are going to be numeric columns. And then there's categorical features, which are either a category, like age buckets, or sometimes they'll be coded as integers. But here we've only got the one, and it's age buckets, which is a categorical feature. So I'm splitting those up. The target column is outcome. Input features is everything that is not the target feature. Then the numeric features, I'm using .select_dtypes and then float column. So this is a list of all of the columns that are not outcome that are floating point numbers. And then we've got our categorical features, which is anything that is not the outcome column, that's either an integer or a category. And you see there's just age buckets, just like we talked about it a minute ago. Now we're going to scale the numeric features. We've already transformed them to make them as symmetrical as possible. So this is pretty simple. We're going to create a scalar object that is the standard scalar from scikit-learn. Then we'll use .fit_transform on all of the numerical features. So here I've got input features, but I'm selecting only the numerical features out of that. And we're doing a fit_transform on all of it. So it's going to fit the scalar and then change all of the data, and I'm calling that scaled_features. Then I'm making that into a data frame so that we can look at it. And the columns are the numerical features, and it has the same index as the original data. So you can see now that all of this stuff has been scaled. It's all different numbers. If you look up here, we had like 2.4, 148, etc. 0.76, now 0.85. So it scaled all of this to be centered over 0 and have a standard deviation of 1. And if we describe it here, we'll see that the mean, these are all really tiny numbers, like 16 decimal places, right? Really, really tiny numbers close to 0. And the standard deviation is all really, really close to 1, which is exactly what we want coming out of the standard scaler. And then if we look at histograms of them, we can now see that they are centered over 0 or close to it, and they're not spread out too much. All of them are like that, see? So this is exactly what we were hoping to get out of using the standard scaler. That's perfect. Now we're also going to look at the correlation, because in general you don't want your numerical features to be correlated. There are some statistical reasons why correlation is bad for modeling. So it's always a good idea to look into it. And we've got some pretty strong correlation here, like between glucose and insulin, or between skin thickness and BMI, or between age and pregnancies. Those are really the big ones, but even some of these, like blood pressure versus age, even this one, which is much lower than those three, is still big enough that it makes me a little worried about using all of these features in the same model. And there are ways that you can get rid of that, but we've learned enough for today. You are going to be asked about removing correlation in this week's mini project, and you can learn a lot by Googling it. And I recommend trying the words correlated features machine learning. Sometimes it's a big deal, sometimes it's not, but I want you to go out there and read about it yourself and decide how much do you actually care about the correlation in your features, and what can you actually do to get rid of it if you want to. Last thing we got to do is one hot encoding the categorical features. So here I said we were going to use pd.getDummies. That is the pandas package, the getDummies function, and we're using the categorical features. And this one, I'm using drop_first equals true. So look at what comes out of this. This gives us age buckets 30s, and they're all 0s and 1s. Age buckets 40 plus, and they're all 0s and 1s. Now if we look back up here at what those buckets meant, right? So each person is in one of those buckets. So this person is in the 40 plus bucket. So in the 40 plus column now, after the encoding, they're going to have a 1. See? A 1 in the first one. Now the second guy up there, second and third actually, are both going to have, both going to be in the 30s buckets. We'll scroll back up and see that. Where is it? There it is. 30s, see? And then this guy, he's under 30. So that means he's going to have both zeros. 0, 0. See? So if they have a 1 in the age buckets 40 plus column, that means that they were originally in the 40 plus bucket. If they have a 1 in the 30s column, that means that they were in the 30s bucket. And if they have both zeros, that means that they were in the under 30 bucket. And that's what drop first equals true does. If you leave this out, it's going to make 3 columns, one that's age buckets underscore under 30, and that it would have a 0 for this row. But if you keep that in, that can mess up some models. So you, generally speaking, you want to do drop first equals true, especially if you're doing linear regression, which again is the kind of model we're going to be focused on next week. So now if we're looking at, this is our 2 buckets and the value counts. We had like 600 people that are not in their 30s, and like almost 200 people that are in their 30s. And we also had more than 500 people that are not over 40, and about 200 people that are over 40. But if you look at people in either category versus no category, okay? So a 1 here means that they're either in their 30s or they're in the 40 plus. This is about even. So that's pretty nice. That sounds good. The last thing we're going to do, we're going to use our 2 trackers, and we're going to make all of this that we've just done over the last 40 minutes repeatable with a function. All right, it was a lot of work, but we don't have to redo it like this every time. Luckily, we can create a Python function that's going to redo like all of the work in a single line. And this is where our trackers come in handy. So our missing values tracker reminds us what we did for each column. So for glucose, we dropped missing values for BMI we dropped. For blood pressure we filled it with the mean, and then for skin thickness and insulin we used a KNN imputer. Remember? That's what the tracker tells us. Then we're making these two functions. The first one, remember, it was when the columns were equal to 0, we said that was a missing value. So this first one, it goes through, all right, it's called recognize underscore missing underscore values. It takes in the raw data frame. Then it's going to go through all of those columns that we said, where we said that 0 was supposed to be a missing value, and it says if it's equal to 0 in that column, replace it with a missing value. So this is something that we did by hand, like individually, up at the top, and now we've just turned it into a function where all we have to do is say recognize missing values in the data, and it does it all for us. Makes it super easy right there. And then the second one, after recognizing the missing values, okay, it goes through, and it's like where we said we dropped the missing values, it drops missing values. Where it says we filled in with the mean, it fills in with the mean. See how this goes? Where we used a KNN imputer, it uses a KNN imputer. And then it turns it back into a data frame at the end and spits it out. So this is just going through all of the stuff that we did through all of the cells up above and doing it like really quickly and easily with a single command. Handle underscore missing underscore values, and it does all the stuff that we just did over the last 40 minutes. Now, the transformation tracker, we're going to do pretty much the same thing. We've got a list of what transformation we did where, but this one's a little more complicated, okay? So, in this one, we've got, what is this, 1, 2, 3, 4, 5 functions. Most of these are about what happens later on. See, there's split data where we split it between target numeric and categorical, and there's scale numeric to use a standard scaler on the numeric data. There's encode categorical, all right, to get the dummies for the categorical features where we're dropping the first one and everything. And then this scale and encode features, this does all 3 of those things. So it takes in transform data, splits it into target numeric and categorical, and then it scales the numeric, it encodes the categorical, it puts all of it back together into one big data frame using pd.concat, and then it returns that. And then the transform data function takes in the filled data after it's been through this function, this missing values function. It takes it in there, starts by making a copy, and then it goes through all of the transformations that we said we did. So like we used the square root for pregnancies and skin thickness. So that's what it does first. Pregnancies equals np.square root pregnancies. And skin thickness is np.square root skin thickness. And then what does it do next? The log. So we used log for BMI and diabetes pedigree function. So down here, BMI equals the log of BMI, and diabetes pedigree function equals the log of diabetes pedigree function. What else did we do? Right, we cut up the age buckets. Now, if you're bucketizing like this, like we are, then you got to create your buckets before you do any other transformation on the age column, right? Because if you transform it, then these like 30 is no longer going to refer to 30 years old anymore. So we're going to do the buckets first using pd.cut. And then we used power transformers for both insulin and the age column. And we're doing both at the same time. This is a power transformer with the Yao-Johnson method. And then we're transforming both insulin and age at the same time using the fit underscore transform method of the power transformer. And so at this point, when we get to here, we've done all of the transformations and everything is as symmetrical as we can make it. The last thing to do is all of this stuff, right? Split the data, scale the numeric data, encode the categorical features, put it all back together as one data frame for the output, and then return that. So that's what this does. Scale and encode features on the transformed data, and then return the transformed data. And then down here we're just testing it out. So we're going to read the data again, raw data straight from the diabetes underscore data.csv, except I am going to make the columns lowercase And then we'll use handle underscore missing underscore values to make the filled data that should have no missing values. So look at this. Doesn't have any missing values. Excellent. And then we're going to transform the data and look at all this stuff. We've got, like we said, the age buckets columns that we created. They're one hot encoded. Everything looks like it's scaled pretty well. Outcome is still 0 and 1s. And then at the end, we're looking at histograms again. So we can see that using our functions, it does everything that we wanted it to do. We've got pregnancies centered around 0 and kind of compressed. Glucose, kind of the same thing. Skin thickness, all of these are looking fairly symmetric, centered over 0, and have a standard deviation of 1, which is exactly what we want. Then we've got our age buckets that are one hot encoded, all 0s are 1s, and of course outcome is binary as well. And there you go. That's pretty much everything that, I mean, there are a lot more techniques, okay? There are a lot more techniques to do this kind of stuff, but I've kind of shared the big important ones that come up over and over and over again. And if you run into any kind of other special situations where you need more than this, then it should be pretty easy to find on the internet. And you're going to practice figuring that out on the internet when you Google how to deal with correlated features in machine learning.
All right, we just went through an entire data set, column by column, and we made each feature, hopefully, as informative as possible. I mean, we dealt with missing values by like dropping them when there were just a couple, or by filling them in with the mean when there were like a few, or when there were like way too many. We used an imputer model of very powerful, meaningful stuff. And we used square root transformations or log transformations to make our data more symmetrical. And when that didn't work, we used the powerful and impressive Yao-Johnson transformation. And when none of those could make our data symmetrical, we just bucketized the column. No matter what came up, we found a way to make our data more useful, more interpretable for a machine learning model or even just for a person looking at it. Now, in this week's mini project, you're going to go through another data set, and you're going to make decisions of what transformations to apply to which column. And more importantly, you're going to explain your transformations. You'll often find that it's not important that you make the best decision. What is important is that you be able to explain why you made your decisions. Now, I hope that you learned something this week. I want you to leave your questions down below, and I want you to go look through the questions below and answer them. You don't need to have all of the answers. You don't need to know everything in order to help somebody else learn, and that's what we're all here for. So if you did learn something, go ahead and like the video, and if you want to keep learning with me, go ahead and subscribe. I'll see you guys next week.